Gotta give it.
Forget about it. Hey yo, at the speed of sound, the world-renowned wax-works compound. So gather round and witness something that is rarely found.
The Database Building Blocks seminar series is filmed in front of a live studio audience. This program is made possible by Google.
Hi guys, welcome back. It's another talk today in our seminar series on building blocks for data systems. So we're excited today to have Sean Smith. He's the founder of GlareDB, and he's been running it since 2022. So he's going to talk about his journey through DataFusion and back. And so we're excited to have him join us. If you have a question for Sean during his talk, please feel free to interrupt him at any time. Ask your question, and don't wait till the very end, because that way he's not talking to himself for an hour on Zoom. Sean, thank you so much for being here. The floor is yours. Go for it.
All right, thank you, Andy. Yeah, I'm excited to be here, and yeah, as Andy said, this talk's going to be really about our usage of DataFusion, where GlareDB is today, and some of the product goals that we're going for, but also what we're going to be doing next with GlareDB, including the removal of DataFusion. It's interesting because I think the CMU tweet that was going out said the talk was going to be about how we're rebuilding GlareDB to use DataFusion. If you're here for that, that's not the right talk, because we're actually going to be removing DataFusion.
That was my fault. Sorry about that.
Yeah, no worries. I just thought it was interesting, but I just kind of get everything straight there. Before we dive in, a bit about myself. I founded GlareDB in 2022, so we've been around for about 2 years at this point. Before GlareDB, I was actually working at Coder, which is another startup where we're developing software for deploying cloud development environments. This allowed organizations to deploy consistent environments for all their engineers so that they didn't have to worry about configuration mismatch or different versions of tooling. And I started there at 2017, so super early on in their lifetime. I was one of the earliest engineers there, working on really every part of the stack, from kind of scaling the back end to a little bit of the front end. And I was there up until I actually started GlareDB. Before Coder, I was actually studying neuroscience at Ohio State. As I was telling Andy, my last year there, I didn't really feel like I wanted to do more school. And so I just kind of decided to say, hey, I'm going to go for a software development job and just go for it and see what happens. And so I did end up at Coder, and it's all worked out thus far. So I'm pretty happy about that. As far as this talk goes, this is going to be kind of split up into two parts. First part is going to be where GlareDB is today. What are our product goals? How did we arrive at what it is we're trying to build? And also our usage of DataFusion. At the end of that, we're going to be kind of covering our challenges with DataFusion, so that'll lead into the second part of this talk, where we're actually going to be going over what we're actually going to be doing for the next iteration of GlareDB, because we're building a new execution engine with the goal of replacing DataFusion. And with that part, we're going to be going through a high-level overview of what that is and how it differs from DataFusion in order to accomplish the goals that we set out for GlareDB. All right, so to get started, what is GlareDB? GlareDB is something, or it's a database system that can join across a bunch of different data sources. Early on, we were actually talking with a bunch of organizations to kind of see what their challenges were. And something that really bubbled up was they have all these data, all this data in different database systems. They have data in MySQL, they have data in Snowflake, Postgres, whatever it is. And they were having to spend a bunch of time managing ETL pipelines and managing infrastructure to move data around before they can actually run any type of analytics on that data. And so what we set out to do is, can we build a database system that can essentially just be a select star from my Postgres database or my Snowflake database or whatever? And the value prop was pretty simple. We just wanted to reduce the reliance on ETL pipelines. We wanted to reduce the infrastructure and labor costs of having to manage that sort of infrastructure. So that's what we're doing. That is what GlareDB is. GlareDB is a database system that can join across a bunch of different data sources. Where GlareDB is today, you can go to our open source repo. We have a very quick walkthrough of actually getting started with a demo Postgres instance where you connect to a Postgres database, you can query from it. And we support a bunch of different data sources already. We support Postgres, Snowflake, BigQuery. We support Parquet files in S3, various data lakes like Delta Lake, Iceberg, etc. We support a bunch of different systems right now. And how we got this far was building on top of existing building blocks. For example, we're working with DataFusion. That's our core. We're using that for our core execution engine. And, as a transit dependency, we're actually building on top of Arrow as well. For storage, we are using Delta RS. And so essentially what GlareDB is a database system that does manage a data lake for you. And so, we chose that because, it existed. We chose DataFusion because it existed. We're a small team. How can we get to a product quickly? And it just felt like those were the right things to use. It allowed us to build a product very quickly and build a proof of concept to make sure this all works. And as far as like choosing DataFusion has a ton of out-of-the-box functionality. It has a SQL planner, it has optimizer, everything for execution, and it has the right extension points for us. Again, GlareDB is a system that can query a bunch of different data sources. It can query Postgres, it can query Snowflake. And what we had to do is just implement a very simple interface. We just had to implement the table provider interface, and DataFusion would do the rest for us. Some of the intangibles are DataFusion has a very active community. There's constant improvements going in. You can go to the repo, you can see the commits that are going in every day. You can see the pull requests. Like, there's a lot of people working on this thing. And given that we were a small team, it just made sense for us to choose something that, was constantly receiving improvements. I was constantly getting better and better and better. And so by choosing DataFusion, we were able to get to a proof of concept very quickly. And we did end up with a working product that we're able to ship. We have our cloud product, which is essentially a hosted GlareDB version that you can use. And then also our Python library, again, that you can use inside your notebooks. And so I'm very happy with where the product is today, because we were able to showcase value, to showcase the value prop that we're going for. However, and now this is probably where the more interesting parts of this talk is going to be coming in. We did face a few issues with DataFusion, including a couple of regressions. Like we try to keep very up to date with DataFusion. Unfortunately, when we did do updates, there were sometimes things that went in that we didn't have control over, and it kind of broke some of our downstream stuff. And sometimes I would end up with a query not working, or an end user trying to run a query that actually produced incorrect results, because we were very invested in DataFusion. We were, implementing custom logical plans. We're implementing custom optimizer rules, and we're implementing custom execution plans for all this sort of stuff. And we would sometimes end up in a situation where a change in DataFusion ended up producing correct results for a query that previously did work. And alongside that, because we picked Delta RS for our storage, trying to upgrade both those at the same time was oftentimes just a huge pain for us, because, Delta RS is depending on DataFusion, and for us, like, we're also depending on DataFusion. And so we had to keep our DataFusion pinned to the DataFusion that Delta RS was on. And sometimes when Delta RS would upgrade their DataFusion, it broke something on our end because we're expecting a certain thing. So, it's just like a mess at times. And it took a lot of engineering work to actually like kind of work through those bugs, work through those sorts of regressions. And, at some point it just starts to wear on you. As I alluded to, sometimes there are correctness issues, especially when it comes to custom optimizer rules, because, for example, DataFusion actually requires unique column names for every column in the query. And if your optimizer rule is actually producing column names that aren't correct or don't match what the upstream optimizer is expecting, you do end up in a situation where you might actually have a plan that is not correct. I was talking to Andy a little bit before this, And we did have a customer that was trying to run a copy to query, trying to copy to just, a very simple join between a Postgres database and a BigQuery database into a Parquet file. And one of the optimizer rules actually completely cut out, that inner part of the query and just replaced it with empty. And so the resulting Parquet file was just an empty Parquet file. And, for us, like that's very concerning. We're a database. Like we can't be producing incorrect results. Like it's important that, if we're going to be producing an incorrect result, like at least do something there, like warn, error, something. And for us to suddenly fail like that was very concerning for us.
So
Now, whether or not,
can you share
yeah, go ahead.
you said okay, when Delta RS would get upgraded, they would
Mhm.
force you to upgrade your version of DataFusion, and then that would introduce bugs where the query is producing wrong results.
Mhm.
Do you know whether those bugs are because the optimizer changed its behavior or because the engine itself changed, and therefore certain quirks or certain behaviors didn't match what they were in the past?
Yeah, I mean, it's a bit of everything, honestly. Like it could be, maybe DataFusion was handling timestamps slightly differently, and an upgrade changed those, and Delta RS didn't change their behavior to match the upstream behavior. And so there might have been like a mismatch between, okay, like what does this timestamp actually mean?
Mhm.
And especially when you do things like column pruning or like just predicate pushdown, sometimes just the rows that are returned back to us are different between versions. And like there's examples like that, and it's very hard to catch everything, right? Like, I'm not going to fault anyone here. It's just software databases are hard. It's very, very difficult to really keep on top of everything. Um, and yeah, so it could be like a change of expectations of what DataFusion is doing, or how certain types are handled, or like it can really be a variety of things for us. And since we actually had customers who are, writing data, we had existing data. We had to kind of keep track of all that. We had to understand how those changes actually, would affect our users, because they had their data stored on our system. We had to make sure our upgrades didn't break any of their existing queries. And that's just a very taxing process for us.
So just to
And
summarize, so it sounds like you're saying it wouldn't be enough to be able to pin the optimizer to a given version. It was the optimizer and the actual engine itself was handling types in a different ways and just simply producing same query plan, but different
Mhm.
results.
Yeah, I mean that DataFusion provides everything, right? It
Yes.
provides the SQL planner, it provides the optimizer. And so when you say, hey, I want to import DataFusion, you're importing an entire version. I think like there's probably the ability to import certain subcomponents of that. Like I'm sure there is, like they split everything up into separate crates. But again, for us, it's like we chose DataFusion because it provided everything for us. And we chose
Mhm.
Delta RS because, again, it provided everything we needed for storage. And Delta RS is depending on DataFusion for a lot of their low-level like predicate pushdown sorts of things. Um, and because we were depending on DataFusion, we needed to make sure we were depending on the same version of DataFusion as Delta RS. And when Delta RS would upgrade, that meant we would have to upgrade. And sometimes we would end up in situations where that upgrade did break existing data that we had. Like,
Got it.
that's kind of the gist of it.
Okay, thanks.
Yeah. And then, kind of interesting, an interesting thing about this as well is like the dependency of all of it. Because, Delta RS is depending on DataFusion. You can't use different versions of DataFusion if you want to use the entirety of Delta RS. And the PR that I actually have linked here is Delta RS actually trying to upgrade to the latest version of DataFusion, and they can't because DataFusion actually introduced a couple different regressions that are causing failures in Delta RS. And this PR has actually been open for a couple months now. I think it was opened in September. And like that's kind of representative of our situation where, hey, like we're trying to upgrade a specific dependency and we can't actually upgrade DataFusion because it breaks Delta RS, or it breaks like we're also depending on Lance for the Lance file format, and Lance actually imports DataFusion as well. And so just like trying to keep everything in sync was very difficult, especially when one of those dependencies would actually break for us. So yeah, like we definitely had a lot of challenges with DataFusion, and beginning of 2024, so earlier this year, January, we actually ended up deciding to say, hey, like, you know what? We're spending a lot of engineering time. We're spending a lot of engineering effort to, try to handle this, to try to manage all these upgrades, to try to, fix all the breakages that are being introduced. And so we ended up deciding to say, hey, like, let's just re-implement it, right? Let's just rewrite it, right? And so that's what GlareDB Next is. GlareDB Next is actually a complete re-implementation of the execution engine. So, like, what exactly are we building? It is a round-up rewrite of GlareDB. We want to completely remove DataFusion from everything. Like, we want to remove DataFusion. We want to remove ArrowRS, and kind of go for that complete ground-up rewrite to build something that really fits in with the features we're trying to provide with the product that we're building. Currently, it is very much work in progress. You can actually go to next.glaredb.com to get like a very simple example of what this is capable of, or you can do a pip install reexec. I will get on to the naming a little bit later. It's all the same thing. Naming's hard. I'm an engineer, so that's kind of what happens. To give you all a sense of where we're at, I do have a TPCH performance graph here. Right now, we are very competitive with DataFusion and DuckDB. There's one or two queries in here where we're doing worse than both, but overall, like the numbers are looking good. I will say there's obviously caveats with this. It's not scientific. I'm just running this on my laptop. I'm currently working through some of the ClickBench stuff to get all that stuff working. But again, like I'm very happy with the performance we're at, and to get all the SQL features we need for TPCH, like we're hitting milestones. I'm pretty excited about it, and we're pretty far along. As far as goals we're aiming for this, we want planning robustness. With DataFusion, again, there's a lot of limitations in terms of how they actually resolve certain columns, how they resolve tables, and how you reference those columns. And so we just want to remove that. We want a very comprehensive and robust planning system so that when an analyst is writing a query and they're used to having that query run in Snowflake or Postgres, we want it to just work for them. And so that's really a goal for us for planning. Like we want those sorts of queries to just work. We also want this to be amenable to hybrid and distributed execution.
Wait, let me stop you there, because
Yeah.
writing a query optimizer is a massive undertaking.
Mhm.
Are you building a cost-based query optimizer to replace the DataFusion entirely?
Yes. So it's not completely cost-based. I'll get, there's a slide on the optimizer
Okay.
in at some point. It's very small, but I can actually go over it right now. It's very heuristic based.
No. If you have slides, go, keep going.
Okay, for sure.
Yeah, thank you.
Yeah, so we have, again, like one of our goals is amenable to hybrid and distributed execution, because we want this thing to be scalable. We want to be easily to scale from your laptop to a cloud environment. And along with that, we need our plans to be completely self-contained. We need those to be independent units of execution for us. With DataFusion, again, there is this implicit dependency on a session context for actually executing these execution plans. For us, we want to be able to just send those plans somewhere else to be executed independently and not have to worry about, hey, does this have a dependency on, certain session variables, or, the number of cores that are on your machine. Like that needs to be handled where it's being executed. And so these plans must be self-contained. They must be amenable to distributed execution. And then we also just want easier dependency management. Honestly, again, like the Delta RS DataFusion upgrade path, like it was always just it was a pain. It was taking up a lot of time and energy. And we just want to avoid that. And then, we also really do want limited extension points here because with DataFusion, again, like the extension is a blessing and a curse. Like we were able to write a lot of features for GlareDB because we were able to extend the logical plans or add in a custom optimizer rule or add in a custom execution plan. But that also did introduce a lot of bugs for us because there are these implicit expectations that, a logical plan produces this type of or these sorts of columns with these sorts of names, or the optimizer rule expects a certain ordering of, plan nodes or, whatever it may be. But as soon as you get off the beaten path, like you're very likely to just hit bugs that are very hard to catch. And so for us with this system, we're not aiming for extensibility. Our extension points are going to be data sources, storage, and user-defined functions. Like that's it. We're not going to be asking you to write a custom physical plan. So, we're not aiming to replace DataFusion as a general purpose execution engine that you can just plug into an existing system. We're writing a full-fledged database here. And then lastly, like we do want portability. One thing that I have found interesting has been WebAssembly and like what does it take to actually like compile a database down to WebAssembly so that you can just deploy in a browser. And for us, like that's a very interesting concept because if we can have a user just be able to try out a database without us having to actually spin up a server for them, like, that's pretty incredible. They can start to see the value right away. They don't have to worry about having to sign up for an account or pay for the infrastructure. They can just try it out. And so I think, honestly, like I think WebAssembly is a very cool technology, and I think it's a very cool technology for databases. And yeah, as I alluded to previously, what's in a name? So when I say reexec, bullet, or GlareDB next, like they're all the same thing. Again, naming's hard. Reexec and bullet are both internal names, for the engine. And as far as like the meaning of these names, reexec was originally the original name for this because I wanted to build an execution engine on top of Rayon to have a push-based scheduler for this. And this isn't a new idea. I think Andrew in the first DataFusion talk actually went into this a little bit, but DataFusion did at one point have a push-based scheduler for this. It was a work-stealing push-based scheduler built on top of Rayon. And yeah, so like this isn't a new idea, but I don't believe they went far enough to actually see if it was a viable alternative to what they're currently doing, which is just async streams on top of Tokyo. And so with reexec, it's just Rayon for execution, right? So that's where the name comes from. Up next is bullet, and this was actually going to be a recent rename, and this one was mostly just a play on words. Bite the bullet. I didn't really want to write a new execution engine. Everyone says that's kind of dumb. If DataFusion's gotten you this far, why not just continue to use it? And there's even tweets up there from Mim saying he likes the decision to just build on top of DataFusion. Like no one wants to spend their life writing an execution engine, but we're doing it. And then also like bullets are faster than arrows, so that's kind of something. But we can get into that a little bit later. And then lastly, the name GlareDB next. This has honestly just been because there's been quite a bit of scope creep with all of this. Originally, reexec/bullet was just supposed to be a replacement for DataFusion for us. We wanted to just plug it into our existing code base and just remove DataFusion. Unfortunately, that's not been the case. We're actually going to be replacing the majority of our code base with this new stuff. Because when we got deeper into, okay, what would it take to actually just kind of shim out the existing DataFusion stuff? There's going to be a lot of work involved because one of the challenges we had with DataFusion was there are these implicit dependencies between optimization and the session context, or execution and the session context. And I didn't really feel like spending the time to write a shim or try to plug that in and figure all that out. And so, hey, like if we're going to be rewriting this thing, like let's start from the ground up. Let's write everything from scratch. Let's figure out how this goes and just go with it, right? So that's where this name comes from, because it's going to be a complete replacement of our existing code base. On the right, you'll see two contributor graphs. The top is the GlareDB repo, and you'll see for 2024, it's kind of flatlined for myself. Like I've only had a couple of contributions to that repo. And then the bottom is the contributors graph for this currently closed source repo, but we'll eventually be open sourcing it. We'll eventually be putting it into the open source repo. But you can see, like, you know, I've been busy at work. I've been doing stuff. I've been writing this thing. And so yeah, that's kind of like where all my work's been going towards. And again, it will replace the existing code base. All right. So yeah, I do want to go through a quick overview of query planning, because this is kind of going to get into the differentiating factors between what it is we're building and what DataFusion actually provides. So again, a quick overview. The input to the system is just going to be a very simple SQL query. We parse it, we resolve it, we do some logical planning, we optimize it, and then we go through this intermediate pipeline planner, eventually leading to an executable pipeline planner, eventually with the output being the executable pipelines. These executable pipelines are what we will actually be executing, and these are completely self-contained. We want these to be completely self-contained to enable distributed execution. We want to run these on remote machines without having to worry about, who planned this, what machine planned this, and we're not going to be hard coding any sort of parallelism inside these pipelines. All right, so first let's go through parsing and resolving. At the top is, we have a very simple SQL query, select star from my table. There's nothing special about this. Like, we're just going to be parsing the syntax tree. The reference is a very basic string, but what we do next is we'll go through that syntax tree again and independently resolve every reference that we find in that syntax tree. And we're doing this outside of any sort of logical planning because we want these to be async. We want these to be independent of any sort of semantic analysis of the query, because our goal, again, is to have those logical plans to be completely self-contained. We don't want any sort of latencies to be cumulative, especially when we're going to be joining across multiple different external data sources. And so we're very much isolating the resolution step from the parsing step from the logical planning step. And we're doing this through generics. One of the pipelines, or one of the building blocks that we're building on, was SQL parser RS. We ended up writing our own parser. It's very much based on SQL parser, but we added an extra generic to all this to enable, to enable this generic for the reference. And so what we do, every node in the tree will have this generic on it so that we can say, hey, is this a unresolved reference or is this a resolved reference? And this is what that generic is, right? Like, that's a very straightforward generic. Like, we're just defining the types for what is the raw statement. And for a lot of these, it's just going to be a string. Like, who cares? We don't know if that table exists. We don't know, if that function exists. But then, we have an alternative implementation which actually contains the completely resolved statements as well. And so that SQL or that syntax tree will be annotated with, catalog entries, file locations, or whatever we need to. And again, that's completely independent of any sort of logical planning. And so what we do is we have this resolver struct, or this resolver type, that has one responsibility. It just resolves that syntax tree. It's not going to be doing anything else. The semantics themselves are very minimal. We don't, again, like I've been saying this, but we don't want that to be contingent on any sort of scoping rules or whatever. We're just going to be looking at the string and say, hey, does this table exist? If it does, we'll look it up in the catalog, and then we'll just plop that catalog entry directly onto the syntax tree. And the output of the resolver is just going to be a fully resolved statement. And what this enables us to do is just send this resolve statement to a remote machine to plan, do whatever we need to do without having to actually like look anything up in the catalog or reach out to external systems. Because a goal with this is we want to reduce the latency of trying to hit these external systems. With DataFusion, we ended up having to fork their stuff to try to make it async. And for us, for example, if we take this, query where we're selecting from a Postgres table, a Snowflake table, and a file in S3, DataFusion is very sequential in how it actually, resolves these things. It's going to be doing it all at the same time as the logical planning. And so we end up with cumulative latencies. And we just want to avoid that. And we also want to avoid async rust. This very much minimizes the amount of async rust for us because personally, like I'm not a huge fan of async rust. You can look at our fork of DataFusion SQL Planner Optimizer or DataFusion's SQL Planner, where we introduce async, and it is not amazing, right? Like there's a lot of recursive async function, which just isn't fun to look at. It's very disgusting. And so we just want to minimize that. We want to minimize the amount of async during planning, and it's just isolated to just this resolving step.
So Hamid asked the question whether you guys considered using Substrate as part of like inputs.
We considered it. I think Substrate's an interesting thing for systems that do want to be interoperable with other execution systems. I think for us, because we're trying to build a very integrated database system, I don't know if it actually makes sense to do Substrate. I think we'll end up exploring it, but internally, I just don't know if it makes sense, right? I don't have anything in these slides, but for distributed execution, we're just using a custom protobuf definition for all of our plans. And because we have a fixed set of operators for us, like it's very easy for us to actually like write everything, and trying to, there just be some amount of impedance mismatch between converting our physical operators to Substrate or even our logical operators to Substrate. But I think at some point we might explore that. Right now, it's not really on our roadmap.
Got it. Thanks.
I have
So
a question.
Sure.
So you're doing resolution, and you're saying you're doing it separately from logical planning. And I think kind of like historically, in the planning step is where you might do some resolution if you're doing things like views or, if what you resolve can affect the overall cost of the plan. So I'm just, as a small peek, like, do you, like, is that just like not an issue for your scenario? Or, if you can just say a little bit about that, that'd be great.
Yeah. So when we resolve, we already know the relative scope of everything that's in the plan. There's minimal semantic analysis to determine if like a select star from reference is referencing a table or referencing an existing CTE, for example. And so for us, we can very quickly determine, hey, if this is a CTE, then okay, we don't need to do anything. If we don't have a CTE with that name, we'll just go to the catalog or we'll reach out to an external system to figure that out, because you don't actually need to go through the entire logical planning step to figure out if something is a table or just a CTE, right? So for us, like we're able to just like very quickly walk through the plan, pull out all the tables, resolve those, and put those catalog entries back into the syntax tree. Does that answer your question?
Yeah. So I think just to summarize, so in your system, you only have like base tables or tables that come directly from a catalog and CTEs, right? Like that's the regime in which like you might like those are your data access paths, right?
So not necessarily. I'm saying table as like a, to kind of, simplify things, but this works for everything from functions, aggregates, files, or whatever. The only real thing that we need to differentiate when we resolve tables is whether or not that is referencing a CTE. And so that's really the amount of semantic analysis that we need to do on the syntax tree. Everything else we can just assume is referencing something in the catalog, and there's a subsystem that we've written to say, if this is not in the catalog, then we'll actually just try to go out to the remote system. Because, for example, if we want to select star from Snowflake table, we'll be able to see, okay, this actually doesn't exist in our internal catalog, but we know that this is trying to reference something from an external system. And so we'll call out to the external system to get everything we need from, that system and bring it back into the syntax tree. So yeah, like this works for everything. This works for functions, it works for files, it works for tables. I'm just saying tables as like a, just to simplify it. If I go
Okay,
to,
that makes sense. Yeah, that all makes sense to me. Thanks.
Yeah, and on this slide with the Astimeta, like this is kind of everything that this currently works for. So it can be everything from a table reference to a table argument to like a copy to destination. So, everything, right? All right,
Great, thanks.
so logical. Mhm. Yeah, so logical planning is, we essentially just take that resolve statement, convert it into a logical operator tree. Nothing super fancy here. But this logical, the resolve statement completely self-contained. And so this logical planning can happen anywhere. It can happen on a laptop, can happen on a remote machine. And also we do implement unnesting arbitrary queries during logical planning. And so we're able to handle various correlated queries and the select statement and the where clause, group bys, etc. And one thing that we do differently from DataFusion is we give every base table in the query a unique identifier, and every column is given an ordinal index. And so throughout the plan, everything is consistent. We know that a specific identifier is pointing to a specific column in a specific table. What DataFusion does instead is it'll actually give every column, or it'll attempt to give every column a unique column identifier, which we'll see shortly actually runs into a couple issues. And one of our goals with that was to avoid the same situation that we're hitting with DataFusion, where sometimes we would end up with a query that would error because a column name or a column identifier was duplicated in the query, and it didn't, it was actually semantically correct query. We wanted to avoid that. So every time we say we're referencing column 0.1, we know exactly what table that's from and what that column index is pointing to. And that's going to be consistent throughout the query. This helps during logical planning and also optimization because we're able to really freely reorder the plan and introduce new nodes into the plan as we optimize, as we optimize and as we kind of change the order of like how things are executed. And we know we're not going to break the output, right? Because we know, hey, this column is going to be pointing to this specific table. And as far as query robustness goes, this is actually a query that I think kind of identifies one of my main gripes with DataFusion, where, again, they expect every column to actually have a unique column identifier. And this is a query that I expect to work in every database system. It works in Postgres, it works in DuckDB, and it also works in our engine, right? But it fails in DataFusion. And this is very representative of the types of queries that an analyst would write. They're not going to be writing, this is frankly like a very simplified example, but you can imagine a scenario where someone is trying to join two tables across two different systems that have overlapping column names. And early on, like DataFusion would actually fail. I will say, the more recent versions actually really helped to address this. Unfortunately, we haven't been able to upgrade, mostly because I've been focused on writing this new engine, and then also, with the Delta RS stuff, like it's actually kind of hard to upgrade for us. But again, this query itself still fails on DataFusion. I don't know if there's a plan to address this or fix this or whatever, but this is something that I do expect to work in a production database system, and it does work in our new system. And this is another example of a query that actually fails in DataFusion. When an analyst is coming into to write SQL, they're going to be writing SQL in a way that just kind of tries to get their intent down onto paper. They don't really care whether or not a subquery is correlated. They're just going to write what makes sense, what's going to get them the results that they're looking for. And in our experience, like we would end up in a situation where an analyst would try to write a query with a correlated subquery in the select statement, and it just wouldn't work. DataFusion, they have some amount of correlated subquery support, but it's very ad hoc. It's very specific to certain places in the query. And given that we implement the unnesting arbitrary queries paper, we're able to more cohesively handle these sorts of queries and everything. We're not prohibited with what sorts of queries we're able to work with, or what correlated queries we're able to work with. All right, and then as far as the optimizer, there's only going to be one slide on this. It's very straightforward. Like we have a bunch of heuristics, expression optimization, filter pushdown, predicate pruning, that sort of stuff. We do implement join ordering from the dynamics programming strikes back, the DP hype algorithm, which does utilize a very simple cost function where we're using the underlying cardinalities, underlying non-distinct values of the tables to produce a proper join ordering for us. One thing that is very different from DataFusion is DataFusion does have optimizers for their logical plans and then an optimizer for their physical plans. We opted to just do for a logical plan because, again, like we're not building something that is super extensible. We're building something that is a completely integrated database system. And if we only have one optimizer step, like that's great for us. We don't have to worry about, hey, like how do we optimize, a completely different type of plan, right? So we just focus on optimizing the logical plan. And importantly for us, the optimization task does not determine parallelism for us, because again, we want query planning to be able to happen on a remote machine, even if it's on a separate machine that is not going to be executing that plan. All right, so I mean, we went through a lot right there, and I know I probably went through a lot of that pretty quickly. And so, if anyone has any questions for the first part of that, like, please chime up, please let me know. Otherwise, we can get started on how does intermediate pipeline planning work and how does executable pipeline planning work? And then finally end with how do we actually execute those?
I mean, you kind of, let's keep going because I mean, how does this? You make it sound like building the optimizer is super easy. There's like, oh yeah, you grab two of Thomas's papers and you bang through it, right? It's no, this is impressive. You guys did this because I don't think anybody else outside of Umbra or CDDB or Hyper does this.
I mean, like DuckDB does a little bit of this.
Sure, yeah. But I think, but this is so Thomas has like this is the older paper. Then he has a newer one where it's like the adaptive join order. Or are you doing that one as well or no?
We're not. That's something I'm looking at, and I'm sure like the next couple of questions are going to be like, do you do like worst case optimal joins? Like, no, we're focused on binary joins right now. I've only looked at the TP hype paper, and with the simple cost function, and so far for the TPCH stuff, like it's working well for us. I'm sure there's going to be scenarios where we're going to be needing to look at something that's a bit more comprehensive, but so far this is working.
I think the adaptive one is like if it goes over like some insane number of joins, and you just fall back to heuristics.
So that's actually interesting because with cross joins, like you can't actually do the dynamic, or you can do the dynamic programming, but what ends up happening is you have a fully connected query graph, and you end up with just a ton of, a ton of possibilities, and you end up, or I believe, if you have a query with 10 plus joins, you end up doing 10,000 pair orderings for the joins, which can take a long time. It can take seconds, and so there's going to be a limit that you want to get to before you just drop back to heuristics, right? Because again, like cross joins, it's very easy to just completely blow that up and completely dwarf the rest of the query here.
All right, in the sake of time, I say keep going.
Can I just ask a quick clarification? So
Go for it.
what you're executing in GlareDB, right? It's essentially going to be executing on whatever. So, like for instance, if you resolve something that goes to Snowflake and you resolve something that goes to Postgres, those will kind of execute in parallel, but ultimately you're going to be executing on like whatever you get back from them, right? So there's just kind of this like two-tier. You're on top of whatever other databases are in the federated system, right? Like that's the full picture, right?
Yeah. I mean, it's very much like, hey, we're just trying to get the underlying data from these other systems, and with Postgres, like we're not trying to push down any sort of joins or any sort of like logic to Postgres. We're saying, hey, like we need this data from this table, and so just give us like the binary copy representation of that data, and we'll do everything on our end. And it's very similar with Snowflake. Like we're doing something similar where we actually just reverse engineered one of their clients so that we can get pretty much arrow data back from Snowflake. Like we're not trying to push down joins to Snowflake. We want to do all the joins on our end.
Great. That helps a lot. Thank you.
Mhm. All right. So yeah, before we get into intermediate pipeline planning, I do want to go over our operators. We do have a fixed set of operators. Again, this is not something that we plan on allowing users to extend other than, maybe the sinks or sources. Right now, we do have a pretty comprehensive set of operators. We don't currently implement window functions or non-union set operators, but those are definitely on the roadmap. We definitely need those at some point. They're just not in yet, but we do have a pretty good number of operators at this point. And then as far as intermediate pipeline planning, what we'll do is we'll just take that logical operator tree and produce some number of intermediate pipelines. An intermediate pipeline is just a list of operators that we're just going to be sending record batches through, right? Like it's going to be a full pipeline. For a join, you'll have a pipeline on the build side, and then for the probe, you'll have a pipeline on the probe plus everything after the join. And we'll also be using the bind context to determine the physical location of the column during execution, because again, like we're not using names to reference columns. And so we're going to have to take that, table reference and column expression and map it back to where exactly that column exists in the underlying batch that we're going to be sending through these pipelines. And as far as operator execution, we're implementing a push-based execution system. And so these operators need to be, kind of be amenable to that. And so every operator actually implements 3 methods for execution. The first is kind of this push method where we push a batch in, and that's going to be, when the operator is actually doing all of its work, whatever it needs to do. We'll have a pull method, which is, hey, give us back the results that you computed. And then we'll have a finalize method for indicating to the operator that you're not going to be receiving any additional data at this point. Whatever you need to do, just finalize it, finish it, and then we'll be just pulling the rest of the results back. And then importantly for this, like parallelism isn't determined during intermediate plan time. We'll actually be determining parallelism by the number of states that we're passing to these operators. And this is important because we want the intermediate pipeline to be completely serializable and executable on, any number of nodes, even on clusters that have machines with different number of cores, or if I want to execute part of that on my laptop, we need to enable those sorts of workloads. And as far as like generating those states, again, this is the executable pipeline planner's job. we'll just be going through that intermediate pipeline, calling this create states function with the number of desired partitions, and it'll be producing the states that we'll be using. And we actually end up with two types of states. We'll end up with a partition state, which is local to the partition. This is essentially pinning that partition state to the thread. And then we'll have a shared operator state that is shared between all partitions for that one operator. And this allows us to really, really take care of ensuring that we're not doing, any extraneous synchronization or anything like that, because we're going to be passing a mutable version of the partition state to the operator. And so they're not going to have to acquire any sort of locks. And if they don't need to, they're not going to be looking at the global state. And as far as like an executable pipeline goes, this is kind of what it is. It's pretty much the intermediate pipeline, just with those additional states. And for those of you who have read the morsel-driven parallelism paper, this is what that is. Like an executable partition pipeline is a morsel for us. We're going to be pinning that pipeline to a thread, and it's going to execute that all the way through. And as far as how this plays into hybrid/distributed execution, what we want, again, is for the intermediate pipeline to be easily serializable so that we can send to a heterogeneous cluster, right? Like we might actually be planning this, planning execution of a query on a machine with 64 cores, but we might be executing part of that on a laptop with only 8 cores, and we need to be able to determine, at execution time, what that parallelism is. And so what we do is we'll just be returning back and forth like that intermediate pipeline. And that enables us to kind of delay determining the parallelism for these plans until they're ready to be executed. And that's going to be the basis for distributed execution for us. All right, so we're at the end. We now have our executable pipelines. What do we do with those? So here we have a trait, the pipeline executor, and this accepts some number of executable pipelines. We currently have 2 implementations. We have a work-stealing rayon-based executor, which is kind of the basis for the name rayexec, where we'll just spin up a rayon thread pool with the number of cores on your system, and we'll just be running through those pipelines and trying to execute them as quickly as we can. And then we have an alternative implementation for the WebAssembly version, where it'll actually just spawn execution pipelines inside of JavaScript promises. And if you go to next.glaredb.com, this is what's being used for that WebAssembly version. And as far as executing a pipeline, if anyone's familiar with async Rust, this method signature is going to be very familiar, because we're just building on top of the primitives provided by async Rust, including the context and pull. And what this is saying is, the partition or the pipeline executor is just going to be calling this pull execute method. And when we get a pull ready okay, we know that that pipeline is done. We don't need to continue to execute it. If we get a pull ready error, that pipeline error, just return that back to the client. If we get a pull pending, that pipeline won't be able to make progress. And what happens internally is the operator will actually store a waker, which will then signal back to the executor when it is ready to make progress. So for example, if we try to execute the probe side of a hash join before we finish the build side, the probe side is going to return pull pending, and it's going to store a waker. And then once the build side actually finishes, that operator will then say, hey, like waker, wake up, begin executing, and then it'll signal to the partition or the pipeline executor to then continue executing that side of the plan. All right, so as far as where we're headed, we do need to reach feature parity with GlareDB before we actually start to ship this, right? Like it's very much a work in progress right now. It's still, a bit and there's still a lot of work to be done for SQL features or functions or even storage and catalog. Like we just got to get through that before we completely replace the existing GlareDB stuff. And then we do want to open source this. We're going to be again completely replacing the existing open source code. And as far as where our cloud deployments are, we're going to be continuing to use the DataFusion stuff until this new stuff is ready to go and feature complete, and we can actually start to ship it and we can say it's ready, right? So it's going to be, I would say, like a couple months before we can say that, but we're making progress. I feel like with where we're at right now, I'm pretty happy with the progress that we've made so far. Honestly, the work on all this has mostly been happening the past 6 months. And to say in 6 months' time, like, hey, we have an engine that, is running the TP-Sage benchmarks and is close to DataFusion DuckDB, like that's pretty exciting. And, just give us 6 more months. Like I'm very excited to see where this thing's going to be. And then as far as limitations, I think DataFusion's a great project. We're just hitting the limits of it. As soon as we went off the beaten path, like it was very difficult to actually add in the features we wanted to in the time frame that we needed. We're a startup, we need to move fast, and to try to wait for DataFusion upgrades or RS upgrades, like it was tough for us. A new engine just needed to happen for us. Like we needed to get out of the dependency mess, and we needed to be able to implement the features we wanted much more quickly. And lastly, choosing building blocks for building a database is hard. You're never going to know until you try. And for us, like we tried DataFusion, we kind of understand its limitations, and that's kind of shaping where we're headed with this next iteration. All right, and so that is everything for us. Open to any sort of questions.
All right, so I will clap on behalf of everyone. I think we have a lot of questions.
Sure.
So Rohit, do you want to go first?
Yeah, thanks for the talk. Quick question about why are you using Tokyo and async when the operators are primarily Rayon based and synchronous? I'm a little confused by this pull execute function signature.
Yeah, so we're not using Tokyo. We're using, like, this is completely executed on Rayon, but we're using the primitives provided by Rust. Rust doesn't provide an async runtime, and so it's safe to say the scheduler that we've implemented on top of Rayon is essentially a very specialized version of an async runtime. Like we're not using Tokyo for this.
Gotcha.
Yeah. Now I will say, we are using Tokyo for some things. We're using Tokyo for a lot of our IO stuff when we're making network requests. That's all happening inside Tokyo because I think Tokyo is a fantastic project for, those sorts of workloads when you're calling out to object store, like it just makes sense, right? And then, interestingly enough, like I actually wanted to completely remove Tokyo from our system, but unfortunately, with how the Rust ecosystem is, Tokyo is very much a hard dependency on a lot of clients, on a lot of database clients that we depend on. And so we needed to design this in a way that enabled us to be able to utilize the Tokyo runtime in conjunction with our own custom execution runtime using Rayon.
Great.
I
Thank
have
you.
a question, Andy.
Sure.
Sean, really
Go
nice
for it.
talk. I was wondering if you had thought about whether instead of building so much of this query execution optimization framework,
Mhm.
If it made sense, and maybe it doesn't, for you to have considered maybe using DuckDB as an abstraction and try to add these pipeline operators that you have to bring data into DuckDB and then use as much of it as possible for doing this type of federated query processing. So I was just curious whether that made sense or if there were reasons why it would not make sense at all.
Yeah, so I mean that's something we considered. I think DuckDB, again, like all these are fantastic projects. I think DuckDB is fantastic at what it does. And for us, as a business, we just kind of had to look at the risks of working with DuckDB, because it's very likely that we can be seen as a competitor to MotherDuck, and we just didn't want to face that situation. You can look at, I believe it's like the PG DuckDB extension where, originally it was going to be backed by Neon and MotherDuck and Hydra, and then Neon backed out because they were just competing interests, right? Like I wanted to avoid that. And then also with a lot of what we want to do, we want this to have distributed execution. Like that is a core component of how we're designing the system. And DuckDB is a fantastic single node system, but I just don't know if trying to make the changes to DuckDB was worth the time versus investing in our own engine. So it would be a logical choice, but for our case, it's just like it made sense to go down this path with a custom engine.
Great, thank you.
Mhm.
Any other questions?
Yeah.
Okay, go for it.
Yeah, hi. So thank you, Sean, for the talk. So
Mhm.
in your talk, you said that, you talked about GlareDB's ability to sort of query across these multiple data sources like Snowflake and Postgres, right? Uh,
Mhm.
we, so with the upcoming engine that's Bullet, and like I was sort of thinking about the things you said about addressing the limitations you encountered with DataFusion. I was
Mhm.
wondering that do you foresee automating SQL-like database operations like query optimizations or schema management or data migrations within Bullet? Like if that is the case, how would you plan to integrate such automation? Because I think automation of SQL databases might be like a hot topic, maybe not now, but like in the foreseeable future.
Yeah, I mean that's interesting. I think for us, like we're very much focused on just like the querying aspect. The
Right.
automation, I don't think we really thought too much about. We do have plans for our cloud stuff to have like automated, CDC pipelines or just like, caching pipelines. But as far as pushing that down to the underlying system, like, we haven't really thought about it. Now, on the other hand, there's definitely use cases for GlareDB that we've developed for inserting data back into the upstream databases, specifically for the reverse ETL for ensuring that those databases have that enriched data. And again, that would be something that would be automated on our end, where we would just be pushing that data back, and not necessarily something that we would be automating on the underlying data sources end, if that makes sense.
But sorry, could you expand on the last sentence that you said?
Yeah, so like one of our goals with data sources is both to read that data so that you can query it, but then also to push data back into those source systems. Because there's a use case for reverse ETL, which is taking that enriched data. For example, if you have data from two different services and both services contain different sets of data, you can combine that data on the GlareDB side, but you might want to actually push that combined / enriched data back into those source services. And so that's very much like a reverse ETL
Got it. Yeah.
workload that we can support.
Yeah. All right. Yeah. All right. Thank you so much.
Mhm.
All right, one last question for anybody else. Otherwise, I'll take it. Although, if I say that, maybe it scares everyone away. So I get, building query objects from scratch. I get that.
Mhm.
Building engine from scratch. And I'm sensitive to, you know, competing against DuckDB or even Polars would be the other one maybe you could have considered,
Yeah.
but they have their own cloud platform. But I'm actually fascinated that like you wrote your own SQL parser. And building an optimizer from scratch is rare, but building the SQL parser itself is even more rare. So what does
Mhm.
your SQL parser do that like the SQL parse library didn't provide? Or what was you sort of said generics? Is that the only thing that it has to be written using generics? So what are they doing that you're not doing? So what are they not doing that you're doing?
Yeah, I mean it's essentially that. Like a lot of what we did with SQL parsing was based on SQL parser. But we did add in that generic, and this was actually an idea taken from Materialize because really enabled us to, again, have that separate resolving step without having to, kind of copy those types into like a separate type. And by having that generic, we can say, hey, we have this unresolved SQL statement. The reference is just a string. We don't know anything about what that table is, where it's from, whether or not it exists. But then, after resolving, we can, using that generic, we can then plug in, the actual like catalog entry of that table. And so we'll have everything there for us. We'll have, the fully resolved entry for that. We'll have the schema of that table. We'll have everything we need. And again, that's like trying to go after this goal of having every step of our query planning to be completely self-contained. And the resolving step is the only step in our system that is actually going to be reaching out to those external data sources. Everything else completely self-contained. And so, we can send that off to a remote system that doesn't have access to the catalog or, even access to these external data sources and be able to generate those executable pipelines that we can then get back and execute those locally.
So you're saying it's like late resolving of the schema, and SQL parse doesn't support that?
Yeah, I mean, SQL parser is it's just parsing SQL.
Yeah.
You're not going to get anything back from that other than, hey, you have an object identifier and that's it. What we're saying is, okay, we need more. We want to be able to add back in like the fully resolved catalog entries or functions back into the syntax tree because we don't want to do that during planning.
Okay. So I mean, so you can do that with SQL parse. It just you have to modify the tree that they spit out. You're saying that like and generics allows you to again do the late injection.
Yeah, I mean the generics are essentially what allows us to do that because we have two different implementations of this estimate. We have the unresolved, which is just the reference is a string, but then we also have the resolved type, which is the reference is a catalog entry. And SQL parser is just, focused on parsing, and so you're just going to be getting strings back, nothing else.
Okay, so you didn't like write your own tokenizer and like grammar file, like.
I mean, we took a lot of inspiration from SQL parser, but
okay,
we did, but a lot of it is based on SQL parser.
Okay. All right, it's a bold move. Very people do this. It's a gross generalization, but you basically have built a system inspired by Thomas Neumann's Hyper or Umbra, like DuckDB, but in Rust, and then with a lot of and similar the same way as DuckDB, you rolled your own everything, right? Rather than taking off-the-shelf parts.
Yeah, I mean this talk was definitely it was interesting because like there's definitely a lot of stuff to cover, but yes, right. Like,
as I said in my email, this is contrarian to the theme of the seminar. So this is fantastic. This is like, okay, like we tried to do it the way the seminar is trying to prescribe, but it doesn't work. So we took our own took your own path. I love this. Yeah. This is awesome.
Yeah, I mean, and I guess to like add some context on that, one of the core components or one of the core things that we're going with this new engine was I wanted to be able to compile it to WebAssembly, and you're not going to be able to do that with DataFusion because of the Tokyo dependency. And for a lot of Rust libraries, there is that hard dependency on Tokyo. And so there's a lot of things that just won't be able to compile to WebAssembly. And sure, Tokyo technically supports WebAssembly, but not in the way that is actually usable, because as soon as you run something that blocks, WebAssembly is going to panic. And so we had to, there's a lot of care taken to ensure that nothing on our end actually blocked. And, that's kind of how all this came about. Like we had to kind of build everything from the ground up to support that use case.